Hello, everybody. This is Matt Calkins here with the follow-up lecture to further discuss and apply some of the concepts in Dr. Ioannidis' lecture. First, as always, my disclosures. I am an investigator in a study that utilizes continuous glucose monitors that are provided by Abbott. Here's a checklist for reading nutritional epidemiology. By the end of this lecture, we will have touched on all 6 of the items here. First, it is always worthwhile to check clinicaltrials.gov for registration, as otherwise you cannot be sure how many associations the researchers have investigated. Second and third, check the method section to see how the exposures, or in our case, nutrients, were collected and the time frame between them. See the food frequency questionnaire lecture for more details. Fourth, keep the researchers honest by making sure that the entire article-wise alpha value, or the risk of a type 1 error or false positive error, is 0.05. Next, investigate the actual effect size by not relying on relative risk and instead calculating the absolute risk reduction or the number needed to treat. Finally, always check the disclosures. This is probably the least important point, however, it is helpful to read research papers with possible biases in mind. The rest of the lecture will be spent discussing point by point Dr. Ioannidis' typical recipe of nutrition research lecture slide with examples. Here is the same list with a slightly different order, and I added subgroup analysis to the post hoc analysis. For the first 2 points, we will do a quick review as I have nothing intelligent to add to what Dr. Ioannidis already said. Let's dive in. This is the correlation globe that Dr. Ioannidis included in his lecture you watched from Module 1. The variables from a food frequency questionnaire sit on the outside of the globe, and the red are the red dots, and each of the green lines is the correlation between these variables. The thickness of the green line is proportional to the absolute value of the correlation coefficient, ranging from -1 to 1. There are 171 correlations, or green lines, between these 19 variables. 94% of the correlations between these 19 continuous variables were statistically significant with a p-value of less than 0.05 for a total of 161 significant correlations. Dr. Ioannidis had another great point about a 169 question food frequency questionnaire. In such a questionnaire, there are 14,196 pairs of variables. He went on to note that 62% of those had statistically significant correlations, which is a total of 8,801. This makes controlling for each individual variable extremely challenging. And Dr. Ioannidis reported that each of these correlations could have fueled one of 1,000 researchers' careers. Next, we'll discuss the large measurement error in nutritional epidemiological studies. First, you can go and watch the food frequency lecture for an in-depth look at the food frequency questionnaires. Dr. Ioannidis also discussed the stability of information in one of his publications. In this figure from that paper, he demonstrates the change in parameters from one food frequency questionnaire that was taken in 1998 to one that was subsequently conducted in 2004 through 2007. During these 2 administrations of the food frequency questionnaires for the same exact subjects 10 years apart, you can see that all variables changed by at least 30%, except for BMI and blood pressure. Here, WG serve is actually the servings of whole grains, which increased to 180%. Keep this graph in mind for later in Module 1 when we review an article whose main data set had one food frequency questionnaire that was completed 10 years before the end of the study. Next, we'll discuss the third part of his recipe. A p-value less than 0.05 is enough to say that a discovery has been made. Many nutritional epidemiological papers convey that a p-value of less than 0.05 is enough to make meaningful conclusions. This can mean 2 things. Nutritional epidemiology publishes small effect sizes that have dubious clinical significance, and that the field frequently suffers from multiple comparisons. First, on the next slide, we will look at 3 examples that deal with small effect sizes. Let's discuss 3 examples of varying effect sizes using epidemiological data. We will start with 3 populations, 3 exposures, and 3 outcomes. For the first population, let's look at the exposure of women being BRCA1 positive. Remember, there's always some error when measuring any exposure in a population with epidemiological data. Dr. Ioannidis rightfully said that this error is extremely small in genetic data, as assays to measure genes are incredibly precise. We will illustrate this with thin lines from the population to the exposure of being BRCA positive. For each of these exposures, we have two outcomes. Ultimately, either breast cancer positivity or not developing breast cancer. Therefore, there are 4 total combinations. These data show that at 70 years old, 87% of women with BRCA1 will develop breast cancer, and 17% without BRCA1 will also go on to develop breast cancer, which we can think of as the baseline rate. Therefore, the relative risk of developing breast cancer while BRCA1 positive is 87% divided by 17%, which is 5.1. The attributable risk is 87% minus 17%, or 70%. Next, let's look at another population with exposure of cigarette smoking. To collect these data, we must rely on surveys from subjects. For this particular data set, researchers divided smokers into greater than 30 cigarettes per day or 0 to 10 cigarettes per day. There is more error in this data collection when compared to the precision of genetic assays, which we will demonstrate as slightly thickened arrows. For example, some subjects might misremember the exact number of cigarettes they smoked, or other inherent biases might affect their answers. Our outcomes will be varied types of lung cancer. Therefore, subjects can either go on to develop lung cancer or not develop lung cancer. In this case, there are also 4 total combinations. When broken down into the different subtypes of lung cancer, there was an odds ratio of 103 for squamous cell carcinoma, an odds ratio of 111 for small cell lung cancer, and an odds ratio of 22 for adenocarcinoma. These are odds ratios as this was a case control study. Because the relative rate of lung cancers is small, these can be thought of as relative risks. Finally, we have our final population. We will investigate this example fully at the end of the module when we have reviewed the paper this data was taken from. Our exposure will be subjects in the upper quintile of red meat consumption and subjects in the lower quintile of red meat consumption. To gather this data, we must rely on food frequency questionnaires, which you saw from the prior lecture are incredibly imprecise. To illustrate this, we will draw extremely large arrows, as many people will be miscategorized into incorrect quintiles. The outcomes we are interested in are colorectal cancer. Again, there are 4 possible combinations. This study had a relative risk of 1.71 or 71% increase. However, the confidence intervals nearly crossed 1. This study was heralded as a substantial and impressive finding. However, the absolute risk was approximately 0.5 over the course of 9 to 10 years. When compared with the above samples, this is an incredibly small effect size that barely reaches significance. In other words, all 3 of these examples are statistically significant. However, it can be argued that only the BRCA and breast cancer and smoking and lung cancer examples are actually clinically significant. Moving on from effect size, this video from Sprightly Pedagogue on YouTube will discuss multiplicity and why it's a problem.
Today is a great day. You're so excited because you finally finished your data collection and it's time to analyze. But there are a ton of interesting questions you could ask of your data. So what do? I guess you'll just dive in and start running a bunch of analyses, right? Please don't. Just don't. Here's why. Many statistical tests use an alpha level of 0.05 as their level of significance. It is critically important to understand that that is the level of significance for only one test. You cannot run multiple tests, each at an alpha level of 0.05, then claim that significant effects were only 5% likely to be due to chance. Each of those analyses has an alpha level of 0.05, but when you step back and look at all of the analyses, the family-wise error rate, as it's called, is actually much higher. Think about it like this. If we rolled a 6-sided die, what is the probability that we would roll a 3? Well, if we only roll it once, the probability will be 1 out of 6, or 0.167. What if we were allowed to just keep rolling until we got a 3? Would it still make sense to say that the probability was 1 out of 6? This is basically like a child who's losing miserably at Monopoly, constantly re-rolling the dice until they finally land on Boardwalk. If you get to keep trying, you have more chances for unlikely events to occur, and your probability increases. It's as easy as that. The family-wise error rate can be calculated with this equation, where alpha sub c is the level of significance for one comparison, and k is the total number of comparisons being conducted. So let's go back to our dice rolls. What is the probability of rolling a 3? If we roll it once, the family-wise error rate is 0.167. If you get 2 tries, it almost doubles to 0.306. By the time you get to 25 rolls, you are near certain to roll a 3. Think of each of these dice rolls like a comparison between the number we want and the number we got. If we want the number 3 and we got the number 6, we didn't match on that trial, but we get to keep trying, remember? If we get to keep doing comparisons, the probability of matching increases. The exact same thing is happening when we're doing a lot of different statistical tests. In this case, the number that we want is really just anything under 0.05. But now let's imagine that we got a 0.08. Here, we as the researchers have a choice. Option 1, stop there and report what was found. Option 2, roll again. What many researchers decide to do in this instance is to run a second analysis. Maybe they'll change out a variable, or perhaps exclude certain cases. It's really important to understand that this is no different than that Monopoly losing child rolling the dice over and over again until they finally get the number that they want. So again, I beg of you, please don't do this. We have options for avoiding the multiple comparisons problem. If the original analysis you were intending to use was a fairly simple one, you may be able to find analyses which consider multiple variables or groups all in one go. For instance, instead of doing 3 t-tests, you might complete one one-way ANOVA. Instead of running 4 regressions, you might just do one multivariate GLM. If you do absolutely have to do multiple comparisons, you can apply a correction to each of those comparisons. This might be something like a Bonferroni correction or a Benjamini-Hochberg. Lastly, Bayesian analyses do not suffer the multiple comparisons problem because they are not using probabilistic thresholds to make significance decisions. Multiple comparisons are a huge problem in science. In my opinion, this is because of our somewhat archaic method of distributing and dispersing data and research to the broader scientific community. Simple steps could be taken, and have begun to be taken, to safeguard against researchers constantly re-rolling the dice. This might include pre-publishing intro and methods sections, including data analytic strategies, with a promise to have the paper published in full upon completion, and following additional peer review of the remaining sections. More than anything, it is incredibly important for the scientific community to realize that there are simply too many easily available options to allow the multiple comparisons problem to continue to muddy our literature.
Next, we'll talk about cherry picking and selective reporting. For these two concerns, keep in mind the end of the food frequency question or lecture, where we demonstrated that investigators can have a near infinite amount of exposures and outcomes. We saw a real-life example of this in Dr. Carroll's video regarding sugary drink consumption and the risk of cancer. As a reminder, this was a Nutrinet Santé cohort that registered 3,300 different food items and beverages as exposures. Against those 3,300 beverages and food items, which you can make 1,000 more nutrient-based exposures with, Nutrinet Santé also collected outcomes on the following: cancers, cardiovascular disease, type 2 diabetes, hypertension, metabolic syndrome, depression, migraines, rheumatoid arthritis, cognitive decline, quality of life, weight, height, mortality, mental health, COVID-19, and multimorbidity. From these associations, we have the paper published and discussed by Dr. Carroll, along with other publications from the Nutrient Sante cohort shown here. For number 6, we have post hoc analysis and subgroup analysis, which I added. The definition of post hoc means occurring or done after the event. In terms of statistical analysis, this means collecting data, reviewing it, then conducting inferences from it. Essentially, researchers can apply an extremely large amount of inferences to a data set after collecting it if they do not have any outcomes registered a priori or before the study was started. You will frequently see this in phase 3 drug trials where the primary endpoint was not met. However, miraculously, there was a subgroup which reached significance. If this subgroup was not pre-specified, it was post hoc. A famous example of a subgroup analysis was shown in the ISIS-2 trial, which studied the effects of aspirin and streptokinase on myocardial infarction and published in Lancet in 1988. The editors at the Lancet wanted to publish numerous subgroups. The researchers, however, knew the perils of this. They ultimately conceded to the editors' demands on one condition. They would include one subgroup of their own, and they decided to include astrological birth signs, with Gemini and Libra being one subgroup and all other birth signs in the other. They ended up showing that all other birth signs, besides Gemini and Libra, had a large benefit from aspirin on vascular death and myocardial infarction. However, unfortunately, Gemini and Libras were born under the wrong retrograde of Mars and did not have any benefit. In reality, this is another example of the multiplicity problem due to numerous subgroup analysis. Current nutritional research is rarely registered. Only randomized controlled trials must be registered. Otherwise, for epidemiological studies, it is up to the discretion of the researchers. As an example to the contrary, the Nutrient Sante cohort was rightfully registered. Registration can mitigate the adverse effects of multiplicity concerns, cherry picking, selective reporting, and post hoc analysis, greatly improving the recipe of nutrition research. Limited data sharing greatly hinders transparency in nutritional epidemiological research. Sharing data would allow multiple researchers to analyze the data sets and even investigate biases that would otherwise have escaped the primary researchers. For anybody who has ever been on Twitter, strong beliefs could be numbers 1 through 11 on this list. Regarding strong beliefs, the old adage of strong opinions weakly held could help improve the discussion of nutrition. At the end of the day, clinicians and researchers are trying to help patients improve the quality of their lives, and it is always important to keep this fact in mind. It is evident that nutritional research can be interpreted many ways because of the degree of imprecision inherent in the research itself. Especially as clinicians, it is important that we have strong opinions so we can discuss patient cases, assessments, and plans with each other thoughtfully with the totality of data. However, these opinions must be weakly held as science advances and new, higher quality evidence emerges. We should use Bayesian statistics to change our belief. On the right, the curve labeled prior is our prior probability, or the probability that our opinion is correct before any new data is introduced. After data is introduced, shown by the black line here, our prior probability changes to our posterior probability. In this way, we move closer to the truth, and the probability that our opinion is correct is much more precise. With nutrition research, where opinions can become very heated, it is important to always ask ourselves, what would it take to change my mind? Many of the conclusions of nutrition research are still questionable. It would be unfortunate if an answer to this question is that nothing would change your opinion. Next is white hat bias. White hat bias essentially means researchers holding strong opinions strongly, causing bias which can lead to the distortion of information due to righteous ends. Dr. Ioannidis has drawn an interesting parallel here with genetic research. Genetic research has suffered many of the same issues as nutritional epidemiological research, given its large reported exposures and outcomes. However, there is no strong belief or white hat bias in genetic research. As he put it, there is no reason to be attached to gene RS1815739 in terms of causing a bias that would affect the outcome, either consciously or subconsciously. And finally, there is strong financial interest. There are too numerous to count episodes of the food industry meddling with nutrition research. One of the more recent ones was the creation of a nonprofit agency called the Global Energy Balance Network in 2014, which subsequently dissolved 1 year later due to public outcry. This organization, which funded obesity research, was actually funded by Coca-Cola, an egregious conflict of interest. The Global Energy Balance Network repeatedly reported that obesity was due to a lack of exercise and not necessarily due to caloric or macronutrient intake alone, thus absolving themselves, Coca-Cola, of all guilt. It was described as an astroturfing organization, which is the practice of promoting a message that seems to come from someone else rather than the original messenger. News of this conflict of interest reached nearly all news outlets. In fact, the fallout reached even academia, with a prominent researcher resigning. From this news article, Coca-Cola promoted the view that, quote, weight-conscious Americans are overly fixated on how much to eat and drink while not paying enough attention to exercise, end quote. And we made it. Points 1 through 11 on the current typical recipe of nutrition research. So when you review future nutritional epidemiological research, keep this checklist in mind. And if whenever you hear the latest food causes or cures cancer on the news, remember these key points. Most nutrients are highly correlated with each other, which makes controlling difficult. There is a high imprecision with our current method of using food frequency questionnaires to collect exposures. Studies are frequently afflicted by multiplicity and post hoc bias. There are underlying conscious and subconscious research bias as well. Finally, the vast majority of epidemiological data is hypothesis generating, meaning we need studies of higher quality to come to conclusions.